we're going to look at power, the rate of energy transfer. And this chapter, when we talk about energy transfer, we're really talking about work. So, I'm going to define power in this chapter as the amount of work we do per unit time. So if I do 10 joules of work in 1 second, I have 10 watts of power. A joule per second is a watt. The other one we have is horsepower if we're talking about really large power. So 1 horsepower is 746 watts. So if it occurs over a time period, I'm going to find my average power by dividing my work by my time. If it's occurring at an instant in time, I'm going to have to figure out what force I'm applying in the direction of motion and multiply it by the speed at that moment in time. Okay? And that will give me something called the instantaneous power. Okay? So let's try 2 examples. The first example we're going to look at is instantaneous power. And so we're going to figure out what is the power of my motor here as it pulls up a 400 kilogram pallet of bricks at a constant speed of 0.75 meters per second. What's the instantaneous power at that moment? And we're going to say it's a constant speed, so our acceleration is 0. That'll make our problem a little easier. So on my object here, I'm trying to find an instantaneous power, so I need a force. Okay. So here is my force that my motor is exerting. Okay. I also have gravity acting on it. And because it's a constant speed, the sum of the forces is going to be 0 in the y direction for us. And so I have the force minus mg equals 0. So the force my motor is applying is equal to the weight of the bricks. So my mass of my bricks times gravity. Now in order to find my instantaneous power, I'm going to take that force, and as long as it's in the same direction as my motion, and these are directions, so they're both going up. The force is pointing up, and so is the velocity, so we'll make those both positive. And so my instantaneous power is going to be mg times my speed. So my power comes out to be 400 times 9.8 times a speed of 0.75. And so my power comes out to be 2,940 watts. Now, if I do want to change that to power, because motors are measured in horsepower here in the States, we end up with 3.94 horsepower, which is a pretty reasonable motor for lifting bricks. Now, this is the minimum power needed. Do you think we'll probably want to have a motor with a little bit larger power in order to make it actually feasible? Yes, we don't want to strain the motor too much. All right. Our second example is when we do work over time. And so our average power is going to be our work divided by time. Now, if you remember, there's 2 ways that you can find work. One way is you can find work by just doing a force times a displacement. And again, this is parallel, and they are directions. The other way is you can use that big, long equation, the work-in kinetic energy theorem. Okay? So we're going to use the work kinetic energy theorem here. And so our problem is, I have a stock boy, or girl, and they're putting cans up on a shelf that's 2 meters high. And each can weighs 0.5 kilograms. And they're going to put 30 cans a minute. I want to know, what is their average power as they're putting all those cans up on that shelf? So the first thing I need to do is find out the work. And so I write out that big, long equation. So I have work in plus work done by friction equals K2 minus K1 plus UG2 minus UG1 plus there's no springs. So what else cancels out? Well, you'll notice that the cans are at rest at the bottom. So K1 goes away because this is my point 1. Here's my point 2. K2 goes away, so there's no change in kinetic energy for the cans. Yes, they're moving in between, but from start to end, there is no change in kinetic energy. We're going to neglect any air resistance on that can. And they start at the bottom, where I'm going to call my height 0. So in reality, all of the work this stock person is doing is going into changing the potential energy of those cans. So their work in is going to be equal to mgh, the mass of the cans. But how many cans? 30 of them. So my total mass is going to be 30 times 0.5, or 15 kilograms. And so my power, average, is going to be that amount of work, mgh, divided by the amount of time it takes them. Okay? And if I use 30 cans, it's going to take them a time of 1 minute. So I can plug in those values. Power average is equal to the mass, which we said was 15 kilograms for 30 cans, times 9.8, times the height, which he lifts them to 2 meters, divided by the time, and we need our time in seconds, because remember, watts is a joule per second. So I'm going to need 60 here, because there's 60 seconds in a minute. I can figure this out, and it turns out that my stock worker is working at about 4.9 watts. Now, it doesn't seem like much, does it, 4.9 watts, considering this light bulb emits energy at a rate of 100 watts. So how many cans would our stock worker have to put up on that shelf in a minute in order to be equivalent to the amount of energy output of this light bulb? And it turns out that it's 612 cans a minute. Okay? So every tenth of a second or so, you better be putting a can from the ground up to a shelf about at head level for you, if you want to be the same as a light bulb.